Hello everyone. For today's advanced concept presentation number 7, we will be going over balloon geometry. My name is Nina, and the materials you will need today is lots of balloons and then possibly some tape. So just a brief background, we will be talking about electron domains today, and they will be represented by using 3D molecular geometry with balloons. And so that can either be a lone pair, single bond, double bond, or even a triple bond and still be represented by one balloon. And so the point of knowing the shapes of a molecule are for a variety of reasons, and they include melting point, density, and reactivity of a molecule, and its influence by its shape. So getting into the purpose of today's interactive presentation is to ideally gain a better understanding of molecular geometry by making a 3D visual representation and also manipulating them with our hands. So we will be discussing a variety of electron domain geometries, and I will indicate 5 things I will be going over as I run through each one, and then here is just a brief rundown of that. So 1 is the total number of electron domains, 2 is the type of molecule, 3 electron domain geometry, 4 number of lone pairs, and then 5 an example. So that will just be a reference point. Also, I just want to go over some brief basics of molecular geometry. So let's get right into it. I pre-blew everything up. So I've got all my balloons here on the ground. It's a party down here. So let's get into the most simplest type of molecule, and this is just a linear molecular geometry, and so it has 2 electron domains with 0 lone pairs, and they are opposing each other because that is the most convenient configuration for them. And an example of this linear would be a hydrogen gas or a carbon monoxide. So now let's get into the next one. So next one is the trigonal planar geometry. So here we can see 1, 2, 3. It's got 3 electron domains with 0 lone pairs, and an example would be sulfur oxide, aka SO2. All right, let's get into the next one. Bringing in an extra. So we've got 1, 2, 3, 4 here. So this is going to be a tetrahedral geometry where we have 4 electron domains with 0 lone pairs. An example of this is going to be methane, also known as CH4. So the next one. Okay. This one, I've got a total of 5, and it is known as a trigonal bipyramidal. And so it's got 5 electron domains, and the example here is a phosphorus pentachloride, also known as PCl5. Okay, so getting into the table in the textbook. So starting with the first one, we here have the trigonal planar. So we've got the 3, 1, 2, 3, and so the total number of electron domains are going to be 3. The type of molecule is a 2, and the number of lone pairs is 1. The placement of lone pairs is going to be in the center here of all 3 of them. where they're all connected. And then the molecular geometry here is bent. And so an example for this one is going to be SO2, also known as sulfur oxide, and this can be found in burnt matches. Okay, so our next one. Next one, we've got a tetrahedral. So we've got 1, 2, 3, 4. The number of electron domains is 4. Type of molecule is AB3 with 1 lone pair. The placement of lone pairs is going to be in the center here. Right there. And then the trigonial pyramidal is the molecular geometry. And then an example of this 4-shaped one is going to be NH3, also known as ammonia. And this can be found in a lot of household cleaners. Alrighty, getting into the next one. This one is also a tetrahedral, so it also has 4 here, as we see. However, the only difference here is its molecular geometry, as it is bent. And so the total number of electron domains is 4, type of molecule is AB2, and then the number of lone pairs is 2. Placement of lone pairs is in the middle here. It's kind of skewed right back here. And there's 2 on each side. So an example of this is going to be H2O. Okay, so now moving into our next one. Okay, so now we are in the trigonial bipyramidal. And we've got 5 here. 1, 2, 3, 4, 5. And here we have 2 triangular pyramids on top of each other. We're looking at it like this. So we take the tehedral we had previously and add a balloon to it. So now it shows 5 lobes of electrons to the 4 orbitals shown previously. So we have a stable structure here and also an axial position with a bond of about 90 degrees and a equatorial position with a bond angle of about 120 degrees combined together. They form a trigonial bipyramidal. And so the total number of electron domain here is 5. Type of molecule is AB4. Number of lone pairs is 1, which results in a seesaw. So let's show that. Removing the 1, and so the number of lone pairs is 1, which, like I said, results in a seesaw. So the lone pair is going to occupy one of the equatorial positions as the balloon of the one I removed results in that seesaw shape. So the placement of lone pairs is a seesaw shape. You can see how they're kind of lined up here. Seesaw. Lone pairs. And so an example for this one is going to be SF4, also known as sulfur tetrafluoride, and it's known as a colorless gas. Alrighty, moving into our next one. I'm going to add this one back in here if it'll stick. Back to 5. And this one is actually going to be the last one for this electron domain geometry. And for this example, it's going to be the same as the last two, trigonial, bipyramidal. However, what's different is going to be the molecular geometry, as this one is going to be linear. But before we get there, we know that a total number of electron domains is 5, as I added the one extra balloon, and then a type of molecule that this is a AB2. The amount of lone pairs are 3. So the placement of 3 lone pairs is going to is going to occur on the equatorial axis. So here we've got 5, and I'm going to attempt to remove 2. Oh, that worked out. Okay. Yay, that worked out. So now I'm down to 3. And so here we are going to be left with a bond angle of 180 degrees, and then we're going to have 2 lone pairs here, here, and here, total of 6. And then an example here is going to be XEF2, xenon difluoride, and this chemical is used in laboratories. Alrighty, moving on to the next. Okay, so here, prop this up like that. Cool. We here have a octahedral, and the lone pairs are always in the axial position, which is why I have it in this positioning where the pink is up, blue is down, and this up down is for stability reasons. So also with this family, there are 2 different molecular geometries that we're going to be going over, and one of them is the square pyramidal and then the square planar. So let's get into the square pyramidal. So we've got our 6 here, and then the electron domain is octahedral, and then the molecular geometry is a square pyramidal, and it has 90-degree bond angles, 6 pair of electrons surrounding the central atom, therefore an extended octet. So total number of electron domains is 6, type of molecule is an AB5, and then the number of lone pairs is 1, and placement of our lone pairs is going to occur on the axial position. Here I am going to just replace this with another example to show you where the location of the lone pairs are. So I removed 1, so we're down to 5 now. And so the lone pair would be at the base. So actually it might be better to just show you on. So we want to keep it in the axial position. So if I were to move this bottom one, we would have our 2 lone pairs right at the base. And then we would have 5 total balloons. Unfortunately, I didn't tape these together, so I can't show that, but I can kind of just show that the base of this would be where the lone pairs would be. With that being said, an example of this would be BRF5, known as bromine pentafluoride. And so that is a colorless liquid, and that's used to make other chemicals, and it's used in rockets. And I know that it's very toxic to inhale. All right, last but not least, we're gonna stick with our 6 balloons here and get into the second molecular shape known as square planar. So this is part of the octahedral family, and it's got 6 total electron domains, and it's made up of 6 equally spaced hybrid orbitals arranged at 90 degrees. The type of molecule is a AB4, and number of lone pairs is 2. So the placement of lone pair is still going to occur on the axial position, which is for stability purposes, as I'd mentioned before. But here, what we're going to do, oh, that worked out. We're going to remove the top one and the bottom one, if I can get it. Excuse this. Okay, that worked out. Oh, that didn't. So we removed the 2 balloons from the axial position, so we have a pair of attached on each side. So we're gonna have 2 here and then 2 on the other side. And then an example for this one is going to be XeF4, xenon tetrafluoride, also another colorless gas used to purify metal. And so that is the electron domain geometry. Hope you guys learned something. Thank you.